Hello there. Today we are going to be talking about radioactive decay, a look into alpha, beta, and gamma radiation. So what is radioactivity? Radioactivity is defined as the spontaneous decay of unstable atomic nuclei through the emission of energy in the form of waves or particles. Atomic nuclei are not always stable. This is due to the inherent conflict between two of the four fundamental forces of nature, electromagnetism and the strong force. Electromagnetism is the force that interacts between two charged particles. Like charges repel each other, and unlike charges attract each other. Therefore, due to the positive charges of the protons in a nucleus, there is a tendency for them to fly apart. However, they are held from flying apart by the strong force, i.e., the strong force is the force that holds together the quarks to create neutrons and protons and holds the two in atomic nuclei. In other words, the protons in the nucleus create a desire of repulsion, while the strong force negates it via a force of attraction. A third force, the weak force, is also responsible for radioactive decay. However, we will get to that later. The discovery of radioactivity. Radioactivity was first discovered by French scientist Henri Becquerel in 1896, when he inadvertently discovered that pitchblende, a mineral rich in uranium, emitted rays that darkened a photographic plate held inside of an opaque envelope. He found that these rays were full of energy, yet they seemed to come out of the pitchblende all but spontaneously, without any energy input. This seeming violation of the law of conservation of energy was explained later by Einstein's famous equation E equals mc squared, which shows that mass has the ability to convert itself into energy. Several other scientists have spent their lives researching and learning more about radiation. Marie Curie and her husband Pierre Curie were two of the foremost pioneers of radioactive research. During their research into radiation, they discovered two new elements, polonium and radium, one named after Marie's home country and the other named after its radiating effects. Here's polonium demonstrated on the left and a sample of radium demonstrated on the right. This research, among other advancements in radioactivity, led to their receiving the Nobel Prize in Physics in 1903 and her receiving the Nobel Prize in Chemistry in 1911. Madame Curie is forever memorialized in chemistry and physics with the Curie, a unit of radioactivity equal to 37 billion decays per second of a radioactive sample. Types of radioactive decay. There are several types of radioactive decay. The three that we will be looking at are alpha decay, beta decay, and gamma decay. Alpha decay, explained simply, is when an unstable nucleus loses a helium nucleus in order to become stable again. This means that the element loses two protons and two neutrons. Due to the inherent loss of protons, this form of decay also changes the identity of the atom. An example of alpha decay is the loss of a helium nucleus in uranium that holds 92 protons, which then becomes thorium, an element with 90 protons. Alpha particles, or the positively charged nucleus of a helium atom emitted from an unstable nucleus, are perhaps the weakest form of radiation, with the ability to not even be able to penetrate a piece of paper. Beta decay is a little more difficult to explain simply. There are two forms of beta decay, beta minus decay and beta plus decay. Beta minus is when a neutron in an unstable nucleus emits an antineutrino, which is a lepton that we will discuss in a later section, and an electron, another lepton. The loss of negative electric charge turns the neutron into a proton, thereby increasing the atomic number of the atom. This type of decay is actually rather famous, with its being the foundation of the carbon dating, the decay of an unstable carbon-14 isotope into a more stable nitrogen-14 isotope. The second kind of beta decay is simply the opposite. A proton inside of an unstable nucleus emits a neutrino and a positron, the opposite of an electron, converting the proton into a neutron and lowering the atomic number of the atom, for example, carbon-10 into boron-10. Now, leptons are the 6 particles shown here in this diagram. Electrons are probably the most famous of the leptons, but they are only one type out of 6. The other one we will look at is the electron neutrino. When a neutron, for example, decays into a proton, a couple of things need to occur. A lot of these have very theoretical explanations, but all things must obey the laws of physics. First, electrons and electron neutrinos always come in pairs. Also, let's assume that the neutron carries a positive and a negative charge, thus causing its neutral state. So in order to lose the negative charge of the neutron and convert itself into a proton, an electron is created and emitted. Yes, an electron is created. This also creates a new conservation law stating that the total amount of leptons must stay the same. The electron causes the net lepton total of the atom to be +1. Therefore, in order to conserve the amount of leptons, an antineutrino is also created and emitted, thus creating a -1 lepton number. In all, the +1 of the electron and the -1 of the antineutrino, a particle of antimatter, creates a zero net change, thus preserving this new law. Beta particles are more dangerous than alpha particles, but can be stopped by a thin aluminum plate. The weak force, as stated, is the main drive behind beta decay, with it being explained as such. W bosons are electrically charged and are designated by their symbols W+, positively charged, and W-, negatively charged. The W boson changes the makeup of particles. By emitting an electrically charged W boson, the weak force changes the flavor of a quark, which causes a proton to change into a neutron, or vice versa, as shown in these images, which we will explore on the next slide. The weak force can convert a down quark, shown here, into an up quark, shown here, and a W- boson, which then decays into an electron and an antineutrino, turning the neutron into a proton, as shown here. The weak force does the opposite with an up quark of a proton, converting it into a down quark and a W+ boson, which then decays into a positron and a neutrino, converting a proton into a neutron. The third type of radiation is gamma decay, which is the most dangerous of the three, with the ability to penetrate several centimeters of lead or even meters of concrete. Gamma rays are part of the electromagnetic spectrum, and therefore are made up of photons. An unstable atomic nucleus might go from a higher energy state to a lower energy state, emitting a high energy photon in the process. However, unlike the other two forms of decay, this form of radioactive decay does not result in the change of element. Therefore, in this example, you start with protactinium and you end with protactinium. The parent and daughter elements are both the same. Now, let's work our way through an example of all three types of radiation in action. So first here, you'll see a uranium-238 atom. Now, uranium-238 is extremely important because its decay from uranium to lead is extremely important in dating of very old objects such as the Earth or the solar system. So here we see uranium-238 going through alpha decay into thorium. Now, at any moment after an atom goes through alpha or beta decay, we have a potential for gamma radiation to be emitted. This is because the very act of emitting an alpha or a beta particle can cause the daughter element to be in a higher energy state, and through the emission of a high energy photon can return to a more stable state. Now we will work our way to protactinium through beta- decay, which, as we see, raises it up on the periodic table due to the turning of a neutron to a proton. And now we work our way up back to uranium. However, we see that 234 is now the atomic mass due to the loss of the alpha particle. And now we go to thorium, now to radium, which is one of the elements that Marie Curie discovered, down to radon and polonium, another one of those elements, to lead, and now we're working our way to bismuth, polonium, lead again, bismuth, polonium, ultimately to lead. So there's a variety of different ways, as we can see, that this element can get to lead, or to mercury, as shown here. And thus we see that radioactive atoms can pass through all different types of decay as they continuously move down the periodic table to more stable elements, or, in the case of uranium as shown here, to lead and to mercury. Radioactivity is an important concept in a variety of fields. Its applications can be applied in physics, in geology, in anthropology, in archaeology, in astronomy, in biology, in medicine, and a variety of other fields. Radioactivity is an important concept in a variety of fields other than physics. For example, The radioactive beta- decay of carbon-14 atoms into nitrogen-14 atoms helps us date remnants of human civilization in anthropology and archaeology up to around 50,000 years ago. Other decay, such as the decay of uranium-238 into lead, as shown on a previous slide, enables us to tackle geological problems and estimate ages up to the age of the solar system. Further, in astronomy we can detect and further understand supernovas through the elements that decay in them that enables us to date the relative rate of the expansion of the universe. Further, radiation is used in a variety of medical treatments, especially of cancer and of other ailments of many systems, with radiation that kills cancer cells and radioactive tracers used to diagnose a variety of ailments such as Alzheimer's disease, tumors, and ailments of the endocrine system. With examples of radiation in action killing cancer cells on the left, and tracers showing the brain function of a patient with Alzheimer's disease. In conclusion, radiation consists of a variety of different types. Alpha decay is the emission of a helium nucleus from an unstable atom, causing the atom to change its identity. These particles are rather weak, not being able to penetrate even a piece of paper. Beta decay is the change of a proton to a neutron, or a neutron to a proton, via the emission of a positron and an electron respectively with their neutrinos antimatter counterparts. Beta particles are more dangerous than alpha particles, being able to penetrate a thin aluminum plate. And gamma decay is the emission of a high-powered photon, which does not change the identity of the atom. These photons are the most dangerous of the three, being able to penetrate several meters into concrete. All three of these different types of radiation have extremely applicable characteristics in a variety of fields, and the work of scientists such as Marie Curie have enabled us to make large scientific advancements that would not have been otherwise possible. Well, that's it for today. Thank you for watching.